The following program is brought to you by Caltech.
Good afternoon, fellow alums and guests. Our keynote speaker this year is as true orange a techer as anyone could imagine. Carver Mead earned his bachelor's, master's, and PhD from Caltech, and then advanced from assistant professor to associate professor to full professor, and now Gordon and Betty Moore Professor Emeritus of Engineering and Applied Science, an association with Caltech spanning more than 60 years. Quoting from the citation with his 2002 National Medal of Technology Award, Dr. Mead was a pioneer in the development of modern microelectronics, from tools and techniques for modern integrated circuit design, to laying the foundation for fabless semiconductor companies, to catalyzing the electronic design automation field, to training generations of engineers, to founding more than 20 companies, including the Actel Corporation, Silicon Compilers, Synaptics, and Sonic Innovations. Along the way, Carver mounted this platform in 2006 to receive the Caltech Distinguished Alumni Award. And on a more personal note, he was the first person to explain to me how a transistor worked in EE3, Introduction to Semiconductor Physics, in the winter of 1969. Dr. Mead has asked that there be no question and answer period following this talk. If you would like to ask questions of him later, there will be a session this afternoon at 5 p.m. Carver?
There's no event that's more convincing to us than this one about the rate of innovation that's happening in the world today. And our alumni, you people here, are at the leading edge of that innovation. And depending a little on how you count, the knowledge base in the world is doubling every 10 years. It's probably not 5, and it's probably not 20, so let's say every 10 years. Personally, I never had a class in anything I did for a living. That's the result of a technology evolution that's running ahead of our ability to do education. I was delighted to see the Distinguished Alumnus Award go to someone who's pioneering in that area. So what do we do in an era where there's nothing you learn in school that's directly relevant to what you do when you get out of school? Well, there's lots of theories about that, of course. One result of having innovation happen that fast is that all of this knowledge is indigestible. So, of course, the natural response to that is specialization. As the old saying goes, you learn more and more about less and less until finally you know everything about nothing. That's not a good answer. Paul made the point that defying the conventional wisdom, finding the places in between fields tend to get insular with time. Knowledge base tends to get kind of crusty and ossified. And it's the gold places are in between the fields, where the disciplines don't have names. So how do you do education in a time when this innovation rate is happening the way it does? Well, there's another role for research in the world. It's not just to go out and find new things. There's another slower and more deliberate process, and that is finding things that used to look different but are actually the same. There are principles underneath. Dick Feynman said it the best. He said, "The real glory of science is that we can find a way of thinking such that the law is evident." Well, if you think about what we did when we got out of school, we went off and we tried to accomplish something out in the real world. And, you know, the stuff we learned in school was vaguely helpful, but when it came right down to it, we had to figure it out our own way and find something that worked and sort of hacked our way through the brush. And then we built real stuff and made it do real things and got a lot of nicks and bruises on the way, and finally got good at what we're doing, and we built up our own little knowledge base. And it was a kind of a little tiny discipline all its own. And there are millions of those. But there's something a little unsatisfying. I know for myself, I always had this vague feeling that I know this thing works, but I'm not quite sure why. And I think all of us have had that feeling down through the years. So that's the role that science has in a world of technology. It's not just to go find out new stuff or make new stuff. It's to figure out what the principles are underneath all that stuff. Einstein said it really well. He said, "As for the search for truth, I know from my own painful searching with its many blind alleys how hard it is to take a reliable step, be it ever so small, towards the understanding of that which is truly significant." And I think each of us has had in our own life those times, the soul searching, that we didn't really understand and we really wanted to. Well, what's the history of reliable steps? It isn't a pretty one. Human knowledge and the development of schools of thought and all is an evolution process. And by their very nature, evolution processes are unruly, chaotic, undisciplined, and fraught with all kinds of messy things having to do with the fact that they're a human endeavor. There are examples that are clear now because we have the benefit of a lot of hindsight. Aristarchus, about 200 BC, had a beautiful model of the solar system with the sun at the center and all the planets in their proper order. And it was lost for about 1,700 years till it got resurrected by Copernicus. And in the meantime, everybody had the Earth in the center. And they were doing epicycles. And it worked, sort of. It worked well enough that nobody had the audacity to say, hey, that really isn't what's true underneath. Hard to imagine that things like that can happen in science, which we all think of as a objective logical discipline. Well, it's not. I can give you a modern example from which we haven't recovered yet. Long about the turn of the century, 100 years ago or so, there was a lot of ferment about natural law, relativity, quantum mechanics. There was a lot of ferment, a lot of discussion of concepts and what way to go at things. But then Bohr came along with his little planetary model of the atom, and that seemed to sort of work for the hydrogen atom. And then Schrödinger came along with his idea that matter was really waves, and you could understand the energy levels of the hydrogen atom because this wave had to go around and come back in phase with itself. So that made a discrete energy. Made perfect sense. But then all the experiments that were going on were all statistical things. You'd get clicks in Geiger counters, and you'd see tracks in cloud chambers, and it looked like there was this sort of particleness to all the things that were happening. And there was this long period of people struggling. Einstein struggled terribly with these issues, more than he did with relativity, in fact. What was going on? It didn't make sense. How could it be a wave and a particle at the same time? How could the interaction it was having be directed somehow? You know, if you calculated how an atom might radiate according to Maxwell's equations, the radiation should go off in all directions. But what really happened was one atom would let go of its energy to end up on another one. One other one. Now, how could that possibly be? So there was all this struggle. So then Bohr came up with this idea. Actually, it was Born that first proposed it. That these amplitudes that Schrödinger was calculating were really probabilities. So you think about that for a while, it got the right answer. And everybody said, wow, that gets the right answer. So it must be right. Now, I don't have to tell you that the second statement doesn't follow from the first. So we have been now about 90 years in a discipline that gets the right answers, that we have basically a computational technique for getting the answers that we observe without a conceptual base that makes sense. And in fact, because of the personalities and egos involved, it became a virtue to not make sense. So what's come of it now is what we call the quantization of the radiation field. You know, the electromagnetic waves aren't really the things we thought they were. They're really quantized. Okay. So where does that take you? Where it takes you is if you just follow your nose like the field has done, it takes you to a place where there are all these virtual pairs, excitations of the quantized radiation field. Well, okay, if there are all those virtual pairs, we ought to be able to see them. Well, so people, of course, look, and that search has been very interesting. The Lamb shift was supposed to come about because of those. And then people that looked at it closely showed that actually the Lamb shift could come about from local interactions of charges and charge distributions inside the atom. And then they said, oh, but it's really the Casimir effect. You know, if you take two gold plates and put them very close to each other, they'll attract each other. And that's the virtual pairs in there pulling on them. And that got put forth as a solution to this effect in 1948. And it wasn't until, let me see, I got to get my dates right here, 2005, a man by the name of Jaffe at MIT showed that no, there aren't any virtual pairs there. That effect is perfectly well explained by the fact that the electrons on the two plates just spontaneously polarize. If there's a little excess negative charge on one side, that'll polarize the other side to have a little excess positive charge, and it's sort of a spontaneous symmetry breaking that gives you that effect. And there's nothing about virtual pairs in there. But there's one thing we do know. If the virtual pairs were out there, they have energy. And that energy, according to any sensible theory of gravitation, will be a source for gravitation. And there are enough of those virtual pairs in that theory to make the universe about the size of the solar system. That's not the universe we see when we look out. That makes the theory off by a factor of 10 to the 100th power. One would think that that would be enough to discredit it. So things can go that far. It's much worse than epicycles, actually. So what do you do when you get in a jam like that? I mean, just keep on chanting the same mantra doesn't make it true. So what do you do? Well, let's go back and see what happened some other times in history when people were able to change the way they thought. About 200 BC, the same general time era where Aristarchus was teaching about the sun-centered solar system, people started making maps. We take maps so for granted that it's hard to imagine there was a time without maps, but there were. And, well, what's so special about maps? Well, what's special about maps is it's an abstraction of an amazing order, because it allows us in our head to get above the earth and look down on it. And in those days, of course, you couldn't go there, so you just had to imagine being there. And that viewpoint, which happened, like I say, just a couple of hundred years BC, completely changed the way people thought. And it happened so totally that none of us even think about it. The people that write about such things don't write about it. It was one of the great transformations in human thought. So if we're going to think about this problem of 10 to the 100th, we better get another way of thinking. Well, it turns out there already is one. In 1908, Minkowski pointed out something which today all of us in science take for granted. He said, we don't live in a world of 3 dimensions. We live in a world of 4 dimensions. So let's just draw what's happening with time as one of the axes and space as one of the other axes, which is really a placeholder for the other 3. And then we can look down on space-time and visualize what's happening without getting caught up in all of our experience of we throw a rock and it splashes later on and that sort of thing. And when you start drawing the interactions that happen to the fundamental interactions, gravitation, electromagnetism, what's called the long-range interactions, you find an amazing thing. You draw that on a Minkowski diagram, and there's an atom here, there's an atom here. It's at a different place and a different time. But the equations tell us that everything on that line, which we call the light cone, that is, everything in the universe you can see, is coupled as if it was local. It's not coupled as strongly if it's further away, but it interacts as if it's local. One way to think about that is you have an atom here that's in an excited state and one here that's in a ground state, and they start interacting. Now, what we always said before was, well, this one shoots out a photon. That's a little bullet carrying energy, and it goes and slams into the other one, and that's the interaction. But there's another way to think about it. The atom that's in an excited state has a ground state, and the atom that's in the ground state has an excited state. And if you mix the two states even slightly, the wave function of the atom starts to go back and forth just a little bit. That's a current which is going back and forth. And that couples to the wave function of every other atom on its light cone. And somewhere on that light cone, there will be an atom that gets just enough of the excited state and gets exactly in phase, and the two start to do this dance. A way of visualizing that is this atom is sending positive energy forward in time. This atom is sending negative energy backward in time. That makes a kind of a standing wave, not the standing wave that you think about, in a waveguide where it's standing still in space and wiggling in time. This is one that's standing still in time on the light cone. And the energy moves from one to the other. And they're both equal partners in this transaction. Well, it turns out if you just start working this out, it gives you a way of thinking so that it isn't mysterious anymore, that wave-like things can do particle-like actions that are directed. So now let's just follow that line of thought a little bit. Ernst Mach had a good idea a long time ago, smart guy. He said, Newton is kind of way off base. Newton had this idea of absolute space. And Mach said, no, there's no absolute space. If you're moving, the only way you know you're moving is you're moving relative to the stuff out there. We would say the rest of the matter in the universe, the distant galaxies. Next step. That means that the inertia of every element of matter comes from its coupling to every other element of matter on its light cone. That is, everything you can see in the universe affects the physics of what you do right now locally. It's a big idea. It's a big concept. Mach was way ahead of his time. People are still arguing about what did mock mean. It's perfectly clear what mock meant. It's just hard to get your head around. But suppose we can swallow really hard, suspend our disbelief, and get our head around that one. Now the factor of 10 to the 100th goes away. The confusion about what's a wave and what's a particle goes away. And we have a way of thinking such that the law is evident. We have something to pass on to the next generation other than confusion. I think Caltech is placed to do that. So I'm working on it.
Thank you, Carver, for that thought-provoking and fascinating discussion. So thank you, everyone, for coming to the 77th Annual Alumni Seminar Day. It's an honor to have you back on campus. Dr. Rosenbaum, we're pleased to welcome you to the Caltech family. I hope you feel how welcome you are here and how excited we are to have you join us. We look forward to your arrival and to helping you connect with the greater alumni community. Thank you for joining us today. So now it's time for you to enjoy your lunch and enjoy the rest of your day. Thanks again for coming.